Good morning. Can you hear me? Let's see who's here. Some people are here. Oh, my screen is lopsided. There you go. I hope you had a great break, a restful, peaceful, spiritual rejuvenation. I certainly needed a break. Good morning. So what I want to do is pick up where we left off. It was the test, right? We did that test together. And the average was good. It was fair. Some people were frustrated and they contacted me. And I promised that I would look at their solutions. So what I did was I went through the questions on the exam and identified the ones that were done relatively poorly. And I tried to rationalize the kind of mistakes that were made. Now, I don't like multiple choice tests. I'm using them because of the fact that I have an obscene amount of work and I don't have a grader or someone who has the time to grade. So we're doing it this way, but I'm taking stock, I'm looking back and seeing where people might have gone wrong, and I did give some half points. So I worked it into the grading scheme for Moodle. So even if you had the wrong answer, you might have gotten half the points if there was a good rationale. So for instance, this question here, I don't even think I gave it half points yet. I have to double check. So this was one of the questions. And so the first one. As we wait for people to come in, not many people, researchers want to determine how the height of a mountain can help explain the temperature. So right at the outset, okay, this first statement, as you reach the top of the mountain, the temperature gets cooler. Cooler is a lower temperature. So this is inverse relationship. This is an inverse relationship. It has a negative correlation. So people forgot that when they answered the question, and all they did was use this number here, 58% for the R square, and then you took the square root but you forgot to put the negative in front. And so you got the wrong answer. I'm going to double check and add half point for that, which is something that I would do if I was grading manually. I'd probably give half points for that. Okay, so I'll double check that. So you'll get some points for that one. And the other thing I noticed is there was some confusion because I omitted this part of the question. And because the questions were randomized, some people might not have seen that part of the question in answering the question. This question was repeated several times, and this part of the, but then the scenario, the setting was repeated in several questions, but the actual question for that setting was changed each time. So I'll have a look at this one as well and see if I can give some points with the misinterpretation. All right, but otherwise, these tests are not worth that much. But if you do better on your final exam, I will move the weight of these tests to the final exam anyways. Okay, so these are meant to just keep you studying and rewarding is meant to reward you for your studying. I don't consider these hard tests. If I need to add some more time, I can even do that. If you guys want an extra hour. The only reason I hesitate to give more time is because we've already made a commitment about how the test would be administered with 3 hours. And if I add another hour, it might disadvantage some people. So I guess I'll see about that. Maybe I'll send an email. Making notes. So about adding more time. So my recommendation is that you complete the test without looking at the alternatives if you can avoid it. Answer the question, then find your alternative or the one that suits you or corresponds to your answer. Sometimes you have to read the alternatives. You have no choice in answering the question, but that's my recommendation. And then have some time to go through the test again and answer the problems in a different way. Use a different mindset, different approach, and see if you get the same answer, okay? And that's the way you should write these tests. For the third test, which is coming up, we're going to focus on Unit 5 and Unit 6. So I'm done with probability. You have to take the time to keep reviewing those problems. I'm going to send you two old exams to study from, or I'll put them on Moodle. They're challenging, and my tests, I have much less questions than the tests I'm getting you to study from, and you need to do the studying so that you can see through these types of questions that I'm giving. They're not as hard as the ones you're studying from, all right? But I don't want that to mislead you. I'm giving you less questions, and they're not as hard. So if you do the work and you start seeing the pattern of how to answer these questions, you won't fall into the common errors. You won't succumb to the common errors people do. Do succumb to. All right. So, any questions about the test? So you have to work with studying the probability material and all the other material. Work with the midterms if you haven't done them all. And like I said, I'll put a couple more finals up. And I want to begin today with the binomial problem, because we're going to focus now exclusively on the binomial variable. Let me see this. Now this is in Moodle. I'm going to double check. I have it as a quiz. I have it included as Unit 5. And it is, just checking, Quiz 512, questions and solutions. No, that's not it. Maybe I don't have it there. I don't have it there because I want to discuss it, but I think I should put it there, shouldn't I? I should... Okay, so I'll put it in Moodle so you have it. So here's the question. Which of the variables defined below are a binomial or have a binomial distribution? Circle the best alternative. Also, define what a success is for the option that you select. Also indicate what N and P are. And if P is, okay, so that P should be precisely given. If it's not, or you can't compute it, but is known. So if P should be precisely given, if it's not, the question should say something like P is known. So that's equivalent to having P. All right, so remember, for a binomial distribution, there are just two parameters that matter. And we discussed this, but now we're going to delve deeper into this topic. So N is the number of independent trials. I'm going to make this bigger. Just try not to cut off the bottom. Okay, so N is they're the number of independent trials, and P is the probability of success on each trial. What we're interested for the binomial is in the variable X, which is the number of successes in N trials, not each one. I want to know all N of them. Okay, so those are the important, that's the variable defined in general, and these are the parameters for the variable. So take some time to go through each of these and figure out which one is actually a binomial. Okay, how did it go? Are you thinking about it? Which one is a binomial? There's only one, A through E. So which would you say is a binomial distribution? Oops, hit my microphone. Okay, someone says D. Nicole says D. How's my sound, by the way? So Nicole says D. Come on, give it a try. So what I try and do in this class is appeal to your intuition first. Okay, so then you realize that at your age, you do have some sense, common sense, that can be applied to statistics. So all I focus on is the clarification of misunderstandings or illogical thinking. And I correct you in your thinking process, and that's just about 10% of what you need, because most of it is fairly intuitive. So given the parameters, my explanation of the parameters, and you having to pick one of these without knowing what I'm going to talk about next precisely, with everything you know so far, you need to be able to identify an N. You need to be able to identify a P. N is the number of independent trials. Trials have to be independent. It means that each time you look for your success, the chance of seeing it has not changed. And P is the chance of a success, should not change. All right, so those are the parameters. No comments? Come on, I have 12 people here. One of them is me, because I have a window open to watch. So at least 10 people here. Make a guess. Make a guess. Have some skin in the game, it said. Then you'll pay more attention to the answer. Okay, Gerardo thinks C and D sound the same. Okay, come on, give me a couple more guesses, a few more guesses, and then I will get into the answer and the approach. I did look, and this is already on the platform. It's in a set of questions and solutions of Unit 5. So I'm not going to post anything else. So you do have this. But I'm going to go through each one now. Come on, guess. Put yourself out there. Take a chance. I'm just cleaning my desk area. Arranging things. I bought some nice furniture to organize everything in here. No other guesses? Okay, Gilberto says C. Is Gilberto right? Is Nicole right? Gerardo's kind of cheating because he thinks he chose two. He thinks those are the same, but they are not the same. One more person. One more guess. So this is really important in understanding what is binomial and what is not. Like when we went through the discussion of what is independent and what is not, right? It's helpful to understand things by knowing what it is not. Okay, Gerardo picks C. All right, so you see what I mean about common sense and intuition. So out of the people who did choose, majority said C. Well, they also said D, so it's hard to pick. But okay, C. Oh, there's Alex. So it's C. The answer is C. All right, that is the answer. So that's the correct one. Now, what's wrong with the others? Let's go through first C, and then we'll go through the others. So C is correct because we take a simple random sample of 25 Puerto Ricans. The probability of having particular blood type is known. So this is the variable, the number you see when you see this, the number of people. So that's the trial, the people going through the list of people with a blood type A. So the sample represents a a set of independent trials. Sorry, I was thinking about something. Yes, it represents the number of independent trials, and then this here refers to the thing we're looking for, the success. So blood type A is the success. And now we can go through this. N is 25, and P, even though I don't know the number, it's said to be known. So that's the best, that's the closest, that fits best to the binomial. So let's go through the other ones. What's wrong with the rest of them? A 911 operator works one day from 9 a.m. until 5 p.m. Okay, the probability of a call is known. So they're saying a call is known, the probability of a call. So they're implying or insinuating that the call is is what you're looking for, a call. However, then it conflates the two. So the call, the probability of a call, and the number of calls are being used for the same thing. So number of calls should be the number of trials, right? But if calls are a trial, then that refutes it being the success I'm looking for. So this is confusing because this is incorrect, or it doesn't fit the binomial landscape because N is not known. Although it says P is known, the problem is N is not known. Because we're going to keep counting calls. That's not a binomial. We're not counting calls. We're going to be counting successes for which the chance of seeing it is known. So it conflates the two. This is a different kind of a variable. It's not a binomial. Okay, let's go to the next one. An airplane carrying 100 passengers has 2 emergency exits, one at the front of the plane and one at the back. The airplane makes an emergency landing and people exit through the door that is closest to them. So let's do the same thing as we did above. I'll do it in a different color. So N, no, I should stick with blue. So N is, the success is going to be exiting the plane, right? And how many people do we have? In this case, n is known. It's 100. We're going to look at people. And but the chance of them exiting is not always the same. People who are closer to a door will exit faster, right? So it's not clear. P is variable. P changes depending on where people are. So it's not the same for everyone, for all the trials of people. So that one fails. So you guys are pretty good. You didn't get tricked by those. C is the correct answer. Let's look at D. So some people chose D. What's wrong with D? Either way, exiting the plane from either one, the people closer to the door are going to have a greater chance of getting out than the people further from the door, right? Whether it's the front or the back door, Nicole. So that's the issue. Changes for everybody. Or it's different for everyone. Okay, let's look at D. You randomly select 5 cards from a standard deck of cards, which contains 13 hearts, 13 diamonds, 13 clubs, and 13 spades. And we're going to count the number of diamonds selected out of 13. So it looks like N is fixed, N is known. Sorry, how many are we selecting? 5, not 13. N is 5. We're selecting 5. Now P, the chance of a diamond, do we know that? So Nicole says it's 1/13, but it's 1/13 on the first try. But its chance changes I'm just looking. Is it 1/13? It's one moment. It's not 1/13, is it? On the first try, it's going to be. Is there 13? Because there's a total of 52 cards in a deck, right? So it's 13 out of 52. Or like I get 52 from 13 times 4 different suit. So that's 1 in 4. So it's a 1 in 4 chance on the first try. But then, once you've picked one, you don't put it back. If you don't put it back, the chance of getting a diamond on the next try changes. It goes down if you already picked a diamond. It goes up if you haven't picked a diamond. So the problem is, again, it changes from try to try to try. So this is not a binomial random variable. The number of diamonds selected is not a binomial. This is actually an example of a hypogeometric random variable. And I give some examples of that. I'm not going to test you in the final or even on the coming test on the hypergeometric, but I want you to identify just a couple of different distributions, because we learned about general discrete distributions, we learned about binomial, we learned about continuous like normal distribution, and standard normal distribution. But what I'm trying to show you is that these do fit other patterns, other kinds of distributions that have been developed for probability research. So this is actually an example of a hypogeometric, and once you know the parameters, you can just plug them into the formula and solve probabilities like this. Identify distributions and then solve probability questions around that distribution. So this is not a binomial. Buen dia, Laura. C is the right answer. Okay, now E is wrong. Why is E wrong? Now that you guys got an idea of how I'm answering these questions, why is E wrong? So E is wrong because there's no N. N is not known, right? Because we aren't fixing N, we're looking for N. So it's conflating again N and the number of trials and X. Really, that's what it's conflating, because X is the number of successes. If you call a success the number of tosses, and then so the number of tosses is the thing of interest over several trials, but the trials stop after you get the tosses of a certain kind. I mean, it's not correct. So N is not known. It ends up being defined by the number of tosses, which is X, so it's not correct. But P, the probability of, on each try, of 7, sum of 7, could be calculated. So P is known, but N is not, so it's not binomial. Questions? What is N? But we don't know how much. See, so it's again, in A, it's conflating. It's mixing up the number of calls to be received, which is not known, and calling that the variable X. So the total number of calls is not known. That's actually what we're looking for. So that's not. This is an example. Let me see something. Yeah. This is an example of a Poisson distribution. So you need a different type of parameter for it, but here you have the time, and you're looking for, over this time, what is the number, what are the number of events that occur during that time? Okay, so this is a different kind of distribution. So when you have a distribution that has an identifiable pattern, you can look at the family of distributions. Let's see if I can do that here. So this graphic shows a set of different distributions that have been developed for estimation by statisticians and people who use statistics in physics and engineering and economics. And you see in actuarial science, these are all the different kinds of distributions and how they relate. And at the heart of it is the normal distribution. But you see up here we have binomial distribution, which comes from Bernoulli. They're all related, interrelated. Here's Poisson over here. And beside the binomial, negative binomials. So these have been developed for different purposes, different settings, okay? And if you don't have if you're setting that you're modeling and then you're going to use for estimation doesn't have a pattern per se, but you have some information empirically, like you've collected data over many years or over a adequate amount of time, and you can come up with what's known as an empirical distribution. You could make your own distribution and use that. So it doesn't so that's that's the idea of that general discrete distribution, where we derived one and we use it to estimate or to plan. Okay. Oh, what happened? All right, there we go. All right. Any questions about this binomial? So that question and answer are on the Moodle page under problems. It's called makeup quizzes, probability in SDS. Yeah, because I would have my students write quizzes in the class when we were in person, and that counted towards their final grade, and I often had to make alternate quizzes because students would struggle with those. So not because they were hard, they were just premature and students didn't have time to study between classes. And I was trying to force them, because statistics is not something you want to study the night before the test. You want to slowly review material and integrate material and synthesize what you knew or what you know and comfortably enter any test. So what I'm going to do now is get into the binomial. Okay, so notation, don't let it bother you. It's meant to help you, so let's just read through it. So the binomial distribution, a variable x is distributed binomial with parameters n and p. Now I'm going to demonstrate how, as long as we know if it's a binomial and we know n and p, we can solve for the probability of seeing any of those possible outcomes, 0 through n successes. So the question being, what's the chance of 2 successes or 4 successes? We'll have a way of calculating that very easily. So where x is the number of successes observed in n independent trials, each observation has only 2 possible outcomes, either success or failure. P is known. It's the probability of observing the success. And then 1 minus P is the probability of observing a failure. And x, we define x as the number of successes in n known, finite, and fixed independent trials. So it's not infinite, and it is always the same, or we set it at the outset. We know it. It's not infinity, and we fix it at the outset. We don't vary it depending on what we're looking for. So for example, n different people are randomly selected and observed to determine whether they are divorced. And we'll call divorce a success. That's not, people wouldn't think that's always successful, but sometimes it actually is. But anyway, that's besides the point. That's what we're looking for, so we call it a success. And different light bulbs are randomly selected off an assembly line to determine whether they are defective or not. The success is looking for a defect, right? So you can define success not as a necessarily normatively good or bad thing, it's just the thing we're interested in. All right, so I'm showing you where we're going with this. So this is really where we're headed. We're going to learn about repairing the distribution for the discrete random variable x that has possible outcomes 0, 1, all the way to n. Right? So repeatedly looking for defective items, you could see 0 defective, 1 defective, all the way to, if you looked 100 times, 100 defects. So this could be a very long table, very long distribution. But what's most important is the pattern. With the pattern that relates for whichever one of those you're looking for, you can solve for the probability of seeing any of those. So I'm going to leave you that for a second. I got to go get some water. So stare at that for a moment, and we're going to discuss the pattern, okay? Give me 2 minutes. Okay, I'm back. So what do you see in the pattern? You see N and you see P. And then you see the pattern repeated with the exponents changing. Oh, sorry. The pattern repeats with the exponents changing. So we have an N, whatever this means. We're going to go through what it all means in a minute. But you see there's a P and a 1 minus P. And then it goes 0, but then it goes 1 and it goes to N. So that just repeats the series. And then the 1 minus P has the exponent N minus 1, and it repeats, but it's going backwards from the most successes to none. Or sorry, the most to none. And then here, this number is scrolling through the series 0, 1 through. Okay, so the pattern is, so what is this? So let's just take one. Let's take it more generally, and let's look at this in this box here. So what do we have here is this P, which means, what does P mean? How do we refer to P? Right? P is a probability of a success. If P is the probability of a success, what's 1 minus P? Close, Manuel. Yes. For the probability of successful outcome. And what's 1 minus P? Right, failure. So we got that. Now let's look at the exponent. So exponent says how many of these are repeating. What's K? K, I refer to K as the special K of interest because you have all these possible things you're interested in. Either you're interested in calculating the probability of no successes, the probability of all N being successful, or anything in between. So that's what K is. K is which one of these we're interested in the table. So I refer to that often as the special K out of the list. You know, like the cereal. Okay, the number of successes out of N we are interested in computing. So that means this is the probability of a success, and this exponent is saying multiply the probability of success times the probability of success times the probability of success, the number of successes we're interested in. And this portion says multiply the probability of failure N minus K times. So what does N minus K mean? And so K is number of successes for this problem. And what's N minus K, everybody? Excellent. Number of failures. Number of failures. And it turns out that K plus N minus K would be the total number of trials, or N, right? So these exponents make n, and these added together make 1. So there, that's the pattern you should always see. Now what's this piece? So let's go, what we're going to do now, what I'm going to do is reemphasize, we're multiplying. Why are we multiplying? Why is this all being multiplied? What principle did you learn so that you could just multiply a bunch of probabilities together? What makes it so that we can multiply all these probabilities together? All right, so you don't know, so I'm going to take some time for this. So let's remember this exercise, this example. Remember, we talked about the variable x as the number of tails observed in flipping 4 coins. And the the possibilities are that you see 0 tails, 1 tail, 2 tails, 3 tails, or 4 tails. And I told you this is an example of a binomial variable with parameters. N is 4 trials, and P is each trial. Each time you're looking for a tail, this is the probability of success. Tail. On each try. And then manually we wrote up all the possibilities and we sorted them into groups, and then I calculated myself that this was 1/16 each, and then we calculated the probabilities for each of these, remember. So that was one approach. What I'm telling you now is there's a pattern here, and that pattern can be exploited so that when we talk about 4,000 flips, we can use that to estimate the probability of certain outcomes. Because with 4,000 flips, we would have to expand this table and we wouldn't have enough paper to write all the possibilities down, or we'd have to use a lot of paper. So rather than doing that, let's see if we can find a formula, develop a formula that reveals the pattern. Okay, so to derive the formula that I just showed you, I want to demonstrate using just this. Let's look at the probability of 2 tails. So I already know the answer. The probability that x equals 2 tails is equal to 6/16. .375. So it's not the answer I'm interested in. It's to show you how to do this in any case, for any n and any p. So let's expand one of these. So we know the result of all of these together, but let's just take one at a time. Let's just look at this one. The probability of a tail and a tail and a head would look like that. Because of, and this is what I was trying to get at when I asked the questions just a moment ago, how do I calculate that? I can calculate that by multiplying the probabilities because of independence. independent trials, it's 0.5 times 0.5 times 0.5 times 0.5. Right? So that's what makes it possible for me to multiply. Now let's write that in terms of the formula that we used before, where P is the probability of success. I can replace two of these with P to the power 2 and replace those two with 1 minus P to the power 2, because a head is a failure. That's 1 minus P, and there's two of them. All right, so all I found in doing that is just this one. But look how many there are. There's 1, 2, 3, 4, 5, 6, because there's 6 different ways of visualizing 2 successes and 2 failures. In high school, you should have learned, and if you didn't, now you're going to see this, you should have learned how it is that you can determine the number of ways of rearranging 2 successes and 2 failures, or 2 T's and H's, 2 H's. You should have learned how you can determine in a formulaic way, with a formula, how many arrangements this results in. So if you didn't, well, if you did, you would have seen something like this. So for example, the number of ways of seeing 2 successes out of 4 trials, that's more important, right? 2 successes out of 4 trials. Not that there's 2 successes and 2 failures, but there's 2 successes out of 4. You would calculate it this way. This is a factorial, use of factorials. It's 4 factorial divided by 2 factorial times 4 minus 2 factorial. This is the basic formula for factorials. And then a factorial is 4 times 3 times 2. And then this reduces to this, and you get 6. So this is one way to find the answer, factorials. Now, I don't expect you to learn this now, if you didn't learn it already, so you don't have to do it that way. We're just going to use our calculator. So pull out your calculator, or you can do this in Excel. This is possible in Excel as well. And you're going to do, it can be written as 4C2 as well. So this is like a matrix, right? But it's not a matrix. It's just one way of writing 4 choose 2. 4 choose 2. 4 choose 2 of the 4. 2 of the 4 are successes. So we write 4 choose 2 on our calculator. I asked you to get this one. You might have a different one, so I'll give you some time to sort it out. The answer is 6. Identify this key over here above the plus is NCR. See this? Okay, so that's where I'm going. So I'm going to hit 4, second function, NCR2, and I get 6. All right, so take a moment to sort out your calculator, and then I'll show you in Excel. If you want to do it the factorial way, you can do that as well. I'm not stopping you. I think I had to hit equals, didn't I? Yeah. Questions so far? So that gives you the number of ways of seeing k successes out of n, and then you multiply by probability of successes, there's k of them, probability of failures, there's n minus k of them, or just the number of failures, and you multiply it all together. Because this 0.0625 is the same for all 6. That's already what we determined before. There's no reason to think, because of independence, those are all have all the same value. I'm talking about each of these have the same value. I just need to know how many there are to figure out the total sum, other probabilities. Any questions? So let's see in Excel if I can do this easy enough. So if I hit equals, where's my equals? Equals. I should have looked at this before. It's not n, it's probably going to be combination. Okay, it's combine or combin. Can you see that? Yeah, you can see that. So combine, and then you hit 4 and 2, and it should be 6. There you go. Okay, so you have different ways. So you can do it in Excel. So the keyword is, the function is combin. Now there's also binomial in here, and I'll show you how to do that. So you can use binomial on Excel, but you do need to know the formula. I need you to know this formula. So it's not, it'll help you check your answer, but I need you to know the formula as well. All right. So with that, in conclusion, the probability of seeing 2 successes out of 4 is the number of ways of seeing 2 successes out of 4 times the probability of successes times the probability of failures for the total number of each. And that is your answer. And that, all we've done with that is solve for this. So we would have to do it for all of them. To get our answer. For it to finish, to complete the table. So let's do that in Excel. So this is going to be binomial now. I'm going to use the binomial function. You have some options, don't you? We just want binomial distribution. That didn't work. I'm going to pick this one. And now, so binomial dot distribution, you have to put the number you're interested in. So that's the K. So the K is going to be 2 successes out of 4 trials, where the probability of a success is 0.5 each time. And I do not want cumulative, so I think I say no. So I just want the value itself. Otherwise, it's going to add up everything before it, and I'll explain that in a second. So this is the answer, you see? So 24.5, and then you have to say 0 because I just want the value for K equals 2. I don't want the value for everything cumulatively before that. If I hit cumulative, I'm going to get I should have just copied it. So the number is 2, 4 trials, 0.5, and if I say cumulative 1, it adds up for K equals 0, 1, 2. It adds them all together for me. This is just for K equals 2. And I'll explain what I mean. So you see, if you add together that would be cumulative. So it's going to add all of these automatically. And you get 6875. Okay? Good. All right, so let's see. I do some more discussion here. Repeating what I just said, reiterating what I just said. I want you to notice something else in the pattern. In terms of this distribution, notice that this is for a distribution that is n is 4 and p is 0.5. It turns out that there's symmetry. You see, these numbers are the same, these numbers are the same, and this is the middle. And we saw that when I discussed this before, that there's that symmetry, and you can draw it. You can draw that distribution as spikes, not a smooth one, right? Because this is discrete, and there's symmetry. Now, why is there symmetry? Will there always be symmetry in binomial? I'll leave you that. I'm going to show you something. So will binomial distributions always be symmetric? So what you can find online are, see this one here, this is an n of 15 and of p of 0.2, and it's slightly right skewed. So it's not necessarily symmetric. Okay, look at this one. This is left skewed, n of 15 and p of 0.8. So binomials are not necessarily symmetric. You can find tables. Here's a symmetric one. And it's not a coincidence. P is 0.5. So if P is 0.5, you will for sure get symmetry. If you look at the pattern of the formula, you'll understand that. But there is another place where you will find symmetry. And we'll talk about that later. I don't know if we get to that today. Maybe we will. Maybe we will. But we're going to talk about that later. But for now, binomial distributions are not always symmetric, but they are if P is 0.5. There is another instance where you will find symmetry that we'll talk about. So with P is 0.5, you see in the pattern, you're just flipping. It doesn't matter what happens in the exponents because the denominator, the base is always going to be 0.5 for either of these, right? So that'll be success. Failure will also be 0.5. And then all you're doing, you're always going to have a total of n all of the time. So this is not going to contribute any difference to the probability for each of the possible outcomes. The thing is going to change the or affect the probability might be this one, but it turns out that the binomial coefficient, that's what this is called, the binomial coefficient is also always symmetric. So the binomial coefficient is always symmetric, but this is only symmetric if P is 0.5. So I have a little discussion over here showing you, demonstrating the binomial coefficient as always symmetric. And I want to take a moment to discuss that so that you don't get caught up with, you'll realize when you're solving the problems and doing the homework, I usually ask you for n choose 0 or n choose 1. Nothing really complicated, although I give you some practice with little more complicated ones. What's most important is that you know there's a pattern here, 1 and 1, 6 and 6, 15, 15 and 20. So the binomial coefficient is symmetric, or they are symmetric. Why do I teach you all these details, right? I'm trying to give you a really strong base so that you could, if you do something different than this, you can actually read about it, and you can read papers, and you you can critically think about how things are being done in research. All right, so what did I want to say? Okay, so what does this mean? 6 choose 1. It means, 6 choose 0. So it means there's 6 possible, there's 6 possibilities. Out of 6, none are successes. So it means that all are failures. How many ways are there of arranging the 6 failures? There's only one way, you see? That's what that means. Let's do the next one. So this is 6 choose 0 equals 1. Let's see, 6 choose 1. What would that be? Well, there's 6 choices and there's 1 success out of 6. How many ways are there of arranging those outcomes? Well, I guess I can have it this way. So you can see all the different ways. I'm just going to show people who don't see it automatically. Basically, I'm just going to scroll this S through, right? So how many ways? 6 ways. All right, so that's how it works. That's the logic. So you might have seen this before, and I'm going to appeal to that and ask you to remember these concepts. But if you never saw it before, I think from what I've described, you can get it now. So if I flipped it and looked over here, if I did 6 out of 6, this is also 1. Why? Because, so 6 choose, so n choose 0 is always 1, and n choose n is always going to be 1. Why? Because all I'm doing here is saying, well, all are successes. How many ways are there of seeing 6 successes? Only one way of arranging them. So there's only 1. And for 6 choose 5, I'm just inverting the S's and the F's to see that this is 6. Questions? Now you don't want to do this every time. You just want to do this. I just want to show you now so that you remember the pattern. So that's 5 successes out of 6. Questions? Okay. All right, so what we've done is prepared you to solve problems. So I have some examples here. Oh, yes. Okay, so let's do this and then we'll get to the examples. Yeah, we have enough time. Just let me think. So I can leave you with those after. And those, and okay, so we'll have time for that maybe. Okay. So remember this problem. 100 cards are presented to an individual being tested for extrasensory perception. There are 4 possibilities: a star, a circle, a wavy line, or a square. If at least 50 cards are correctly guessed, a person will be considered to have ESP. So what we want to do is find I go through the process here to practice using the calculator. But what I really want to do is the third one. What is the probability that someone who is simply guessing will be found to have ESP? So for all the problems, the probability will be 0.25 and n will be 100. And what we want to find is this. So we have a long table of values, right? We would have to find each of these in that table. X equals 50, x equals 51, x equals 100. Remember, this is a discrete distribution, so we can calculate each of these. And then we want to sum them. Now this is very time consuming. However, it's very important that we be able to calculate this probability. So you could use Excel to do something like this, right? You could set it up, but even that is rather tedious. Until computers were invented, statisticians appealed to other methods approximating this value. Okay, so I'm going to teach you how to do that. So you should practice these calculations on your own. Make sure you can make these calculations. But this is where we're heading next. So I did mention there are tables. We could make, like I said, we can make this in Excel. But you need to learn how to do the approximation, so you still need to understand the formulaic approach. All right, so let's do some problems here together before I continue. You have all the answers. Unit 5 and Unit 6, I give you the answers for everything. The only unit that I didn't give you all the answers was maybe normal distribution, but I think I give you the answers for everything in the notes otherwise. Or somewhere. I do this. I solve them online in the normal distribution part. All right, so let's see. If a fair die is rolled 6 times, the probability of obtaining exactly 1/5 is equal to what? So you have to interpret the problem now. Now this is not just about finding n and p and plugging it in a formula. You have to interpret what they're looking for, right? So is this a binomial? So if you can satisfy if you can find each of those and define a success, it's a binomial. So what would x and pk be? And what would be the success in this problem? So Nicole, what would be X and P and K and success? Oh, you're saying what the success is? Okay. Okay, successes. Okay, success. Success. Okay, so now the biggest problem students have here is distinguishing between each trial and the total of the trials. When I'm talking about X, I'm talking about the total after looking at all n trials. When I'm talking about success, I'm talking about each trial. Okay, so success is on each trial. On each trial, I'm looking for 5. Out of the total trials, I could have gotten 0, 1, 2, 3, 4, 5, or 6. Notice there's always a 0, okay? So I could have no 5s up to 6 5s. All of those are possible. But the one I'm really interested in to solve this problem is I want exactly 1. So K is equal to 1. N is equal to 6, right? And P, what's P? P is the probability of success. It's the probability of a 5 on each trial. My question is, what is P? Manuel's right. So it's the chance of seeing 5. Any of the possible outcomes have the same chance with rolling a die, a fair die. So it's 1/6. Now you shouldn't take the 1/6 and put it in your calculator because you're going to lose some of the decimal places. We need to work with 1/6 as a fraction. And what we want to solve for, our special K is 1, so what we want to find is the probability X equals 1. So that is, remembering the formula, the number of trials is 6, and we're looking for 1 success out of 6. Can you hear my stomach growling? The probability of a success is 1/6, and we are interested in 1 success exactly. The probability of a failure is 5/6, and the remainder, if 1 is a success, that leaves 5 failures. That's how I want you to set up this formula. This component is not a fraction. It means N choose R on your calculator. So we just discussed any N choose 1, it's always N. This is going to be 6. This is 1/6 because anything to the power of 1 is itself. And the only thing we really have to punch into our calculator is the last. So these will cancel, and that will leave that amount. So you can do this manually when you solve your next test, And then you can also check it in Excel to make sure you got it right. Okay, but I'd like you to practice manually to catch yourself in making any mistakes. And there are some exercises where I asked you about the formula, so you need to know the formula. So what's the answer? Any questions? All right, when you put it together, the answer is 0.4. Does anybody need me to show them how to punch this into your calculator? So if we punch this in, it's 5 divided by 6 equals power 5. 0.4. I'll do that again. Oops, I'll do that again. 5 divide 6 equals y to the x 5. In probability problems, in binomial and prob, and anything that has to do with the probability, any probability for this class, I like you to round to 4 decimal places, but the options are not always 4 decimal places. But for final answers, we will put 0.4019 in this case. In general, use 4 decimal places. Okay, let's work on the next one. Again, let's identify if it's binomial, right? X and P, K, and success. So tell me what you know here. This one's easier because we've already dealt with this one. I'm going to do the first one. Sorry, I'm going to do the first one in Excel. So it was equals, and we have to start typing binomial, and then we pick distribution, and we tell it that we are interested in 1 success out of 6 trials with a probability of 1 over 6. Can I put that in there? I think 1 divides 6. I don't know. We'll see if it works. And I do not want cumulative. I just want the single value. It worked. Okay, so this was the problem we just did. So Oh, sorry, show you what I wrote. That's what I wrote. So you shouldn't round you shouldn't get the decimal value for a repeating decimal number, okay? Just use the fraction for it. So I don't usually teach with Excel in in-person class, but it's different now, so you can use Excel if you like. All right, let's try the next one. And the fraction can be done in the calculator. I did the fraction in the calculator. I don't think this calculator has a fraction like the other. There's another calculator I have that has a fraction. I think you just have to put it in brackets here. The other calculator that I was using for some of the videos is the TI 30XA. And it had a fraction. You could actually enter a fraction on the screen and work with it. I don't think that's here. So I just did 5 divided by 6 equals, and then power 5. Okay, so help me with this one. Okay, so no, x is not 5. X is always the total possible outcomes, right? So it's going to be 0, 1, 2, 3, or 4, because n is 4 flips, and the probability of what's a success? What are we looking for here? We're looking for heads. On each trial, we look for a head, and then we tally how many we see. Out of 4, the possibility each time of a head is 0.5. But the possibility of one head out of 4 is a different number. Okay? That's a different concept. That would be using k as 1. So which k are we interested in here? Are we interested in 0, 1, 2, 3, or 4? Well, it says no fewer than 2 heads. No fewer than 2 heads. Which one corresponds to no fewer than 2 heads here? No fewer than 2 would be, it could be 2 heads, 3 heads, or 4 heads. So this means I have to calculate k as 2, or x as 2, x as 3, and x as 4, and add them together, right? This is a discrete distribution. I have to add the probabilities to know what no fewer than heads would be. So k is equal to 2, 3, and 4, and then we sum them to get the answer. So we have to calculate x equals 2, x equals 3, and x equals 4. So again, distinguishing between what happens each time and the total of all 4 times, or n times, you have to distinguish between these concepts. So just exploiting the pattern here. So all I'm going to do, it's going to be 2 here, 3 here, and 4 here. It's going to be 2 here, 3 here, and 4 here. And 2 successes leaves 2 failures. 3 successes leaves 1 failure, and 4 successes leaves 0 failure. You see the pattern? And again, you can put those in Excel, or let's practice with the calculator. We can simplify a bit before we go to the calculator, because we know that these ones simplify. This one will be 4, this one will be 1. And it's just 0.5 all around, so this is 4, and this is 4. It's always going to be 4. Remember the discussion I had about when it's 0.5, the exponents don't really matter too much. So the only one we have to punch in our calculator is 4 choose 2, because this is also 0.4. We already know 4 choose 2 though, it's 6. So if you don't know what I'm doing right now by simplifying, you have to go through step by step. So let's do that, let's do this in our calculator. 4 choose 2. So 4 second function NCR2 equals, and then you multiply by, you have to use a bracket, 0.5 to the power of 4 each time. So we already saw this number, right? For x equals 2, it's 0.375. So one more time. So 4 second function NCR2 equals times bracket 0.5 to the power 4 close bracket, 0.375. So these numbers should be familiar because we did this for tails, but it's the same sort of thing. This is 375. This one is going to be 4 times that. Four times brackets 0.5 to 4 is 0.25. And this is just 0.5 to the power of 4. And the answer is the sum of all of these. Let's see, let's do that in Excel now. So let's try for n equals 2. And p equals 0.5. We calculated for 2, 3, and 4. Remember, I'm using an iPad on Excel, so if it's anything different on yours, if there's anything really different on yours and you're confused, let me know, but it should be similar, same even. Just the appearance looks different because you can see my keyboard. X equals, and the menu looks different to me. So we're going to put equals binomial and get the distribution one, that was this one, and then we put in that it's 4, no, we don't want 4, we want 2, and then trials are 4, and then probability is 0.5, and we don't want cumulative, no. And then we could actually copy that and just change one number because there's a pattern. And just edit that this is not 2 that you're interested in, but 3. And this is not 2 that you're interested, but 4. And then you can sum. forgot to put the equals. Equals sum. Okay, questions? All right, let's see if we can do a couple more together and then I'm gonna move on. Why don't you try these two? Okay, let's look. Suppose that 60% of a herd of cattle is infected with a disease. So X is the random variable representing the number of cattle that are infected. In a sample of size 5, let Y denote the number of cattle that are not infected. So what is Y's distribution? Is it binomial? Well, yes, because I could find N and P, and X is the total number of not infected cattle out of 5, right? So the P would be, which P? So which one is it? If infected is 60%, then not infected is the complement. So it's, oh, not that one. It's 0.4. Good. Okay, next one. An African hospital is treating patients who have this fever. 70% of patients with the disease die, and each patient lives or dies independently of other patients. There are currently 7 fever patients in the hospital. The probability that 6 patients or less die is. So, let's see. I'll give you same approach. Is it a binomial? If so, what's X, N, P, K? And how do you define success? Okay, so there's 7 patients that we're going to observe. So those are our trials. So it's, yes, 0, 1, 2, 3, 4, 5, 6, and 7. And so that's N is 7. And the chance, so what we're interested in is important now. What are we interested in? You get it by the end of the last sentence, right? Usually the probability that the 6 die. We're looking at death, unfortunately. So success is death. And the probability of success for each patient is known to be 0.7. So that's from here. And what do we want to find? So that's the K. Usually it comes just down to the K. So what's the K? There are 7 fever patients in the hospital. The probability 6 or less die. Okay, so K would be equal to 6 or less. Or, what's another way to do this? Find the probability that X equals 7 and take it away from 1. Because it's complement, right? Those are the possibilities. Those are the possibilities. I want these, but if I find 7 and I take it away from 1, that's the same thing. Because they must sum to 1. So that's much easier, isn't it? So finding the probability X equals 7 is N, which is 7, choose 7, because that's the K. And then the probability is 0.7, lots of sevens in this problem, to the 7, and then, so that's success. Failure is 0.3, and no failures. Okay, so let's review. This is success, this is failure, this is number of successes, this is the number of failures. If it's 7 successes, that's what you get. So this is going to be 1, and this is also going to be 1, so all you have to compute on your calculator is 0.7 to the power of 7. Or use Excel. And use Excel. Do them both. Practice with both, right? Practice with both. And we're going to do one more of these, and then I will talk about the next subject. Let's finish this. 0.7 to the power of 7 is 0.0823. I'm going to keep a lot of decimal places because I'm not finished yet. I need to take this away from 1. So this is equal to 1 minus 0.082353. So the best answer is 92. If you round to 2 decimal places. So hold the decimal places till the end, and then you find the best answer. Okay. So that wasn't so hard. Tease apart all the elements, and then answer the question. If we put this in Excel, you see it's relatively easy. All you need are the components, the parameters, and NP. And obviously you have to put K in there. So for K, you would just have to you would have to know what to do. This is what I mean about, you need to understand this whole thing before you start using Excel, right? So you could have used Excel and calculated all of these and added them together. Or calculated this one and subtracted it from 1. So I'm not going to do it. You guys can practice that. So let's do the last one I want to do together, and this is about SARS. What a coincidence. But SARS. And then I'm going to leave you to finish these. The answers are all here. Also, the homework for binomial in Moodle, I have placed, and let me show you. I'm going to take this camera off. I do that by accident. Off. I touch things by accident. Okay, I want to show you in Moodle. Did I close it? So what I've done in the course site for Unit 5. No, I think I have it at the top here. So I have it, homework. So here, no, that's homework. That's all the solutions, right? So up here you have all the homework solutions here in a document. But then I also have the solutions for binomial. I believe I must have put them here. Let's see if I did. Yeah, see? This is the document of the solutions for the homework for just the bin part. And I solve all of the problems with x, n, and p. Okay. Okay, so you should practice those on your own. Now that you have an idea, if you need any help with that, please let me know. All right, let's do the SARS problem and then I'll leave it to you. Is it a binomial? If it is, you should be able to identify x, n, p, k, and success. Good work, Manuel, in answering my questions. Let's see, can you do this one? It's often useful or intuitive to begin with n. What is the n? Okay, x. Okay, so n. Okay, there are 4 patients. So those are who we're going to observe. We're going to observe 4 patients. Suppose the probability of a patient requiring emergency attention. So emergency attention looks like it's what we're looking for, right? Or no, what is it we're looking for? Suppose the probability at any one time of a patient requiring emergency attention by a staff. So that's the number they gave us, unfortunately. So that's going to be the 0.4, sorry, that's going to be the P. So this is the probability of requiring emergency attention. I'm summarizing. So this is the requiring emergency attention. And the chance is 0.3. Assume patients behave independently. So that means just because one requires emergency attention doesn't mean that another one does. What is the probability at any one time that there will not be sufficient staff to attend? So we need to interpret that question in terms of how we have laid out the problem. Either none, 1, 2, 3, or 4 will require emergency attention overall. Which of those aligns with not sufficient staff? Not having sufficient staff. That's the question. That's the K in there. So there will not be sufficient staff and here's the information on the staff here. There are 2 staff. So there will not be sufficient staff if more than 2. So, okay, there's an assumption in here that's not clear. So assuming 1 staff member is required for emergencies. That's kind of implicit in there that you just need 1 person, 1 staff member. So which of these options, 0, 1, 2, 3, 4, corresponds to will not have sufficient staff? Exactly. So these 2, if 3 or 4 need attention, we're in trouble, right? There not be sufficient staff. So we have to calculate the probability of 3 or 4 and add them together for the answer. Now, I had to make that assumption because it's not clear. Maybe you need 2 staff for emergency attention. But we'll just say 1. Make it less complicated. Okay, so that's all we have to do. Then we calculate the probability x equals 3. And actually, you know what I'm going to do is make it zoom it in. So remembering the pattern, successes, this is the probability of success. Wait, what's the probability of success? Is it 0.4 or 0.3? I'm using the wrong number. Sorry about that. Let's fix that. And then that makes the other one change as well. Sorry about that. So for individuals, if 3 need staff, probability is 0.3 of needing attention. So that's 3 successes, 1 not needing attention. That's the probability of attention, not needing attention. So again, these have to sum to 1, and these have to sum to 4. And then you add that to 4 needing attention. Remember, this becomes 4, and this becomes 1. So it's very simplified. This becomes 1 as well. So punching this into your calculator, which you should practice, so, you know, I'm teaching you the statistics. You guys have to work on the math, okay? So you got to practice entering that and getting your answer. So the answer and notice among the options, the first one appears, but that's just the first part. That's not the final answer. So the final answer to this so this is really an important calculation, isn't it? Because it shows the chance that you're not going to have sufficient staff and the likelihood or the risk and someone dying because of insufficient staff. And it's about 10%. It's 8% anyway. So need I stress how important statistics are? Okay. So work on, if you don't have any questions, work on the rest. Also work on the homework exercises. And there's some more problems. Oh, I created other problems as well with solutions in Moodle that you can practice. So that's not so hard once you get working with it. You know how to do it in Excel. Here's an example of binomial tables you can find online. So before calculators were everywhere, in universities and in engineering offices, people had tables of probabilities for binomial distribution. And the P would be along this axis and the N would be down here. And then for, these were set up as cumulative tables. You could also have the one that we're pretty much developing is where you just have each of the values, but these are cumulative. This means 0 out of 15 with a P of 0.05. This means 1 out of 15 with a P of 0.5. And then this one means with 1 out of 15 or 0 out of 15. So it adds together this one with whatever was here. Anyway. And you see they quickly become one because the probability is so low. Anyway, so these tables, you see the probability is going up. And that's what was done before we had computers, and now people have Excel. You don't even need to use a calculator, but I want you to learn the formula because it's useful. As you saw in the table, I demonstrated all the connection between all the different distributions. Binomial is at the heart of sampling, so it's really important that you know it. All right, so there's some other problems here that I give you solutions for, so try these. You have the answers for those that I give you, and some more discussion, and that brings us here. I'm going to start here. So I'm going to pick up where I mentioned, what do we do in the case that we want to approximate the answer? If we have to add a lot of the probabilities in the distribution together, it becomes cumbersome when you're talking about thousands, an n of 1,000 or 10,000 or 1,000,000, right? It's better to have an alternative method rather than having to make tables and tables of values that you're going to sum. So statisticians developed a method of approximation, and they based it on what I'm going to tell you about right now. So it begins with this distribution. Let's look at this distribution here. So this is the binomial distribution with n equals 5 and p equals 0.4. Not exactly symmetric, roughly symmetric, right? Well, where is the balancing point of that distribution? In other words, where's the expected value of that distribution? No idea, right? Doesn't it look like 2 is the balancing point? Okay, let's be more rigorous about it. Well, first I want to use a different example, and then I'll come back to this. Here's my different example. If a basketball player makes 80% of his free throws, you can expect that on 10 tries, he would get how many free throws? So if it's 80%, chance of him getting a free throw or getting it in the basket, and he tries 10 times, what would you approximate the numbers he's going to get, the number of free throws he's going to succeed in, to say basketball talk, I don't know, in 10 tries? So out of 10 tries, how many baskets will the basketball player get? Nobody. I'm waiting. Are you there? Nicole says 8. Right? That makes sense. It's 80%. If we know this in advance, it's 80% of, and remember when we say the word of, it's always multiply. Okay. I'll fix that because it might be confusing. So when you say of, multiply. Okay, so what are we doing then? We have multiplied and found a mean. What mean are we finding? We're finding the mean of a binomial distribution. In this case, the binomial x has a chance, so where the chance of success is making a basket out of 10, with the chance being 80%, x is a binomial, right? Okay, making a free throw. So to get that average with this information, what we did was multiplied these two. So I'm going to introduce a new notation, but it looks similar to what we did before, but it's just to clarify. You don't have to even use it, but it's just to clarify because I'm going to introduce other types of variables in a little bit, all next class. So I'm going to use mu x, that's the mean, which is just n times p. All right, everybody's okay with that? So now let's take that down to the other distribution. Let's take that property down here. Given you have the information that the probability of a success is 0.4 and you try and look for it 5 times, then the mean should just be n times p, so it turns out to actually be 2. So theoretically it's 2, visually it's 2, right? So you need to remember that. So we have a binomial. We can extract from here a concept of the mean. We can get a mean. We can also get a standard deviation. Now, I'm not going to prove this by intuition, but this can be derived by theory. And I believe I have it in the notes how to derive this. But what for now you need to remember this. Actually, I created a formula sheet at the end of these notes, Unit 5 and Unit 6, that has all this information from now on, like all the formulas that I show you, because it can get, they all look similar, it can be confusing, so I tease them apart right at the outset for you. So next class we're going to start with that formula sheet in front of you. So this is the formula for the standard deviation. This is the formula for the mean. So the mean of x is n times p. So again, you're using the parameters, right? And the standard deviation of the distribution is np 1 minus p with a square root around it. So the variance is this. If that is important to you, you know it. Okay, so it turns out, I think I proved these. I think I proved it over here. Yeah, I proved it on the page before. You can have a look at that to understand what I've done, and I've used the rules of mean and variances to derive these properties. But I also explained at least the mean to you intuitively. Okay. So before we go, I want to say one thing and then I'm going to go. It turns out that even though this is not symmetric, and that's partly because this is 0.4, but it's not the case that P has to be 0.5 to be symmetric. I said there would be another way. This is this other way that you will find a symmetric binomial distribution. If it turns out that n times p is more than 10 and n times 1 minus p is more than or equal to 10, in fact, it turns out not only is the distribution symmetric, but it's approximately normally distributed. So it turns out we know the mean and standard deviation. I just showed you, well, I demonstrated them to you. I showed you them and I gave you a page to look at how they're derived. But this means approximately here. So it turns out if you can verify that a binomial distribution has an n times p greater than or equal to 10 and n times 1 minus p greater than or equal to 10, then that binomial actually is approximately normal. And why is that useful? Well, we learned a lot about the normal distribution. So we're going to appeal to the normal distribution with a mean and a standard deviation to answer questions about what to expect. All right, so I'm going to leave you with that. I'm going to ask you to read through all of this stuff and do the binomial problems, read through all this stuff, and I'm going to start next class on page 25. Maybe on page 23. So read through all of these and we will start here next class, okay? And so up to page 25, and then you can do the exercises. There's lots of stuff for you to do here. And then I'm going to get into the sampling distribution. So next week we're going to have, so let's see, April 17 will be SDS, and then and I'm going to start inference. So that's Unit 5 and Unit 6 will start. And then April 24, May 1st, and May 8th, sorry, we're going to focus on Unit 6. And we need to talk about when we're going to have the final exam. So we'll talk about that next week, because I have to look at what they have on the schedule and see what you guys think we can do. Because if we have 3.5 classes for Unit 6, that's pretty good. But I could still give you another week to study. All right? So any questions? Well, I said I will start here, so you guys read on your own what exactly I did, because that's really just a review of the normal distribution with the preliminary step of checking. So do that by yourself, and then I'm going to start here next week. Okay, page 25. And you guys can work on all the problems. And at the end of the notes, you'll see the formula sheet that we're going to work with. Oh, where is it? There it is. So what I've taught you just now is captured in number 1. So we've done this so far. Not bad. This is all you're going to need for the rest of the class. So we're already on to studying for the final exam. Well, the third test and the final exam. Any questions? May 1st. May 1st, the test will be after the class, right? Usually I use it for a review. So, yeah. After the class, we'll have test 3. The test is after. And I mentioned today, if you guys want more time, I'm going to send an email about that. If you want more time for the test. I don't have much problem with giving more time. I just want to make sure that students don't feel it's unfair because they have made commitments after the class time, the test time. Okay, so with that, I say goodbye. Have a great weekend, a good week. Keep in touch. Let me know if you want to meet with me. We can do office hours online. Okay, bye.